Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Fazullah, and in this lecture, we shall study the complex power series, its radius of convergence, and interval of convergence. So, let us start from the definition of the complex power series. A series of the form summation an z minus z naught power n, where n is from 0 to infinity, is called a power series centered at the point z naught. If we expand this series, we get, if I put n is equal to 0 here and here, I will get a naught plus a1 z minus z naught and plus a2 z minus z naught square and plus up to so on. So here in this series, the coefficients an are some real or complex numbers, and z naught is a fixed point. Z naught, this is some fixed point which is called center of the power series. And now in this series, if I put z naught equal to 0, I will get a series of the form summation an z power n, where n is from 0 to infinity. And if I expand this, I will get a naught plus a1 z plus a2 z square and plus up to so on. So this is a series centered at 0. This is some particular form of this one, because if we put z naught here, we automatically get this series. Now let us show you some examples of the power series. Example is that one power series is this one, summation z power n divided by n factorial, where n is from 0 to infinity. If I put 0 here and here, I will get 1. If I put 1 here and here, I will get z. If I put 2 here and here, I will get z square divided by 2 factorial up to so on. So this is a particular power series whose center is 0. And now let us see another example. In this example, let us take another series of the form this one, z minus 3 whole power n divided by n, where n is, or let us, this is n plus 1, so then we can take n from 0 to infinity. And now if I put the values, I will get, if I put 0 here and here, I will get 1. If I put 1 here and here, I will get z minus 3 divided by 2. If I put 2 here and here, I will get z minus 3 whole square divided by 3 and plus up to so on. Sometimes we are given a function and we have to find its power series. So let us see an example that how we can find a power series from a given function. So from a given function, let us solve an example. The example is, find the power series of number 1. The function is f of z is equal to 1 over 4 minus z, but about about z is equal to 0. And number 2, we have to find the power series of the same function, but its center is at 1. Then how we can find the power series? So let us solve this example. First of all, to solve part number 1, we usually use here the binomial expansion. The binomial expansion is that 1 minus x power minus 1 is equal to 1 plus x square and plus up to so on. So now let us take the first part of this example, where f of z is equal to 1 over 4 minus z. And now I have to take 4 common from this one. So I will get 1 over 4 into 1 minus z divided by 4. And after the simplification, I will get 1 over 4 into 1 minus z divided by 4 whole power minus 1. Now I can use this expansion. So from this one I will get 1 over 4 into 1 plus z by 4 plus z square divided by 4 square and plus up to so on. And now if I multiply 1 over 4 inside, so I will get that f of z is equal to 1 over 4 plus z divided by 4 square plus z square divided by 4 cube and plus up to so on. If I write this in the summation notation, I will get that this is equal to summation z power n divided by n plus 1, where divided by 4 power n plus 1, where n is from 0 to infinity. So this is the required power series for the given function f of z, whose center is at z is equal to 0. Now for this you will see later that the radius of convergence of this thing is 4. So if I draw the graph of this curve, its center is at 0. The center is at the origin. And its radius is 4, so this point is now 4. This point is 4, and this is the origin, 0, 0. So this is 1, 2, 3, and 4. This is the required. So basically, this series is convergent inside this disk. And later we will check some other thing, that whether it is convergent on a radius 4 or not. So we will learn this after some time. And now let us see how we can find the power series of that function when the center is at 1. So let us do the process again for the next question. Now here again f of z is equal to 1 over 4 minus z. I have to split 4 such that I have to get the center 1, z minus 1. So I can write this thing that this is equal to 3 minus of z minus 1. And now I have to take 3 as common. So I will get, that 1 over 3 into 1 minus z minus 1 divided by 3. And in the next step, after simplification, I will get that f of z is equal to 1 over 3 into 1 minus z minus 1 divided by 3 whole power minus 1. And again I have to use this binomial expansion, and I can get that this is equal to 1 over 3 into 1 plus z minus 1 divided by 3 plus z minus 1 square divided by 3 square and plus up to so on. If I multiply this 1 over 3 inside, I will get 1 over 3 plus z minus 1 divided by 3 square plus z minus 1 square divided by 3 cube and plus up to so on. So if I express this in the summation notations, I will get that this is equal to z minus 1 power n divided by 3 power n plus 1, where n is from 0 to infinity. So now you can see that this is a power series whose center is at z is equal to 1. And its radius, of course, you will learn after some time that how we can obtain the radius of convergence. So its radius is 3. If I draw the graph of this curve, then its center is at 1. So let this is 1. This is origin and this is 1. And its radius is 3. So 1, 2, 3. Similarly 1, 2, 3. So I can get a curve of the form this. Now again this is 4. This one is 4. So this is the required circle or disk for the given curve. So this power series is convergent inside this disk, and outside of this disk it is divergent. So this is all. Thank you. Now let us see that what do we mean by the radius of convergence and how we can find the radius of convergence of a power series. So you can see from the definition that if we are given a power series of the form this one, then there exists a real number r. There exists some number r. If z minus z naught absolute is less than r, then this series is convergent. And if this is greater than r, then this series is divergent. And that number r is called the radius of convergence. So basically this z minus z naught absolute less than r will give us this disk, that inside this disk our power series must be convergent, and if you go away outside of the disk, then the series will be divergent. And now let us find the methods which we will use to find that number r. So let us see this. Finding the radius of convergence. Finding the radius of convergence r. So there are two methods which we can use and find that number r. The first method is the ratio test, and the second is the root test. So the first method, we know that from the ratio test, if we take limit n approaches to infinity, a n plus 1 divided by a n absolute, and if we evaluate this, we will get some number r. And now from that number, some number L, and from that number L, we can get r. So r will be equal to 1 over that number L. So this is radius of convergence for a power series. Similarly, this is just like this is the ratio test. We can also use the root test, and by the root test we can evaluate the limits n approaches to infinity, nth root of a n, and we can find L. And then again, radius of convergence r is equal to 1 over L. So this one is called the root test. Now we have to solve some example to find that number r. So let us find some example. The example is find radius of convergence for the power series. The power series is given as summation 2 power n z power 2n, where n is from 0 to infinity. So let us see that how we can find the radius of convergence. First of all, we have to write an from here. So this coefficient, this is an. So here an is equal to 2 power n, and from this we can obtain that an plus 1 is equal to 2 power n plus 1. And now we can find L, which is equal to limit n approaches to infinity and an plus 1 divided by an absolute. So just putting values and you will see that limit n approaches to infinity, n plus 1 is 2 power n plus 1 divided by 2n. And if I simplify this and evaluate the limits, we will get 2. So now in this case, L is equal to 2. So what will be the radius of convergence? So the radius of convergence in this case is equal to 1 over L. So just putting the values, we get that R is equal to 1 over 2, which is the required answer, or radius of convergence for this example. Now let us solve another example. For example, and you can see that in this example, you can see that the center is at 0. But we have to find another example in which the center is not 0. So let us find another example. Again, another example is we have to find radius of convergence of the series. The series is summation n is from 0 to infinity and 4 power n divided by n, 4 power n divided by n into z minus 3 whole power n. So let us find radius of convergence for this power series. Again here, in a similar procedure, we can find an, which is equal to 4 power n divided by n. From this we can find an plus 1, which is equal to 4 power n plus 1 divided by n plus 1. And now let us find L. L is equal to limit n approaches to infinity, an plus 1 divided by an. And now let us put the values. We get limit n approaches to infinity. N plus 1 is 4 power n plus 1 divided by n plus 1. Divided by an, so I will inverse this thing and we will get that this is n divided by 4 power n. So if I simplify this thing, I will get that limit n approaches to infinity. From here I will get 4. And from here I will get n divided by n plus 1. So if I apply the limits, you can see this is infinity by infinity form, which is an indeterminate form, so you can use the L'Hopital rule. Or the other procedure is that you have to divide the numerator and denominator by n, and you will get that limit n approaches to infinity 4 into 1 divided by 1 plus 1 over n. And now if you apply the limits, so you will get that the answer is 4. So in this example you can see that our L is 4, so what will be R? R is equal to 1 over L. So from this we can get that the radius of convergence for this power series is 1 over 4. That's all. Now let us see interval of convergence. Let R be the radius of convergence of a complex power series of the form this one. Then we know that if R is the radius of convergence, then Z minus Z naught absolute is less than R. And if we simplify this thing, we get this thing, which is interval of convergence. But here is a condition that the series may or may not be convergent at the end point this one and at the end point this one. That is why if we have to find the interval of convergence, first of all we have to reach to this place and obtain this thing. So half work will be done to that point. Next we have to put Z is equal to Z naught minus R in the given power series, and we have to check whether the series is convergent at this point or not. Then we have to put Z is equal to Z naught plus R in the given power series, and we have to check whether the given series is convergent at this point or not. So let us solve an example from which it will be clear that how we can find interval of convergence. So the example is find the radius of convergence and interval of convergence of the complex power series Z power n divided by n, where n is from 1 to infinity. Okay, this is the given series, and we have to solve there whether what is the radius of convergence and interval of the convergence. Okay, so here again an is equal to 1 over n, and from this I can obtain that an plus 1 is equal to 1 over n plus 1. And now I have to find L. So L is equal to limit n approaches to infinity, an plus 1 divided by an absolute. And if I put values, I will get limit n approaches to infinity. An plus 1 is 1 over n plus 1. And n is 1 over n, so if I take the inverse of this thing, I will get n over 1. And now we have to evaluate the limits. So if I apply the limits, again this is infinity by infinity form, so we can use the L'Hopital rule, or we can divide the numerator and denominator by n. So we get that this is equal to limit n approaches to infinity and 1 divided by 1 plus 1 over n. And from this we get that L is equal to 1. So now a radius of convergence is 1 over L, so we get that R is equal to 1. In the next step we have to find a radius interval of convergence. So to find interval of convergence, here we have to use that Z minus Z naught is less than R, but Z naught in this power series is 0. It is centered at 0. So we can put values, and from the values we can get that Z absolute is less than 1, where R is equal to 1. And from this we can obtain that minus 1 is less than Z and Z is less than 1. So half work is done. But now we have to check whether the given series is convergent at this point or not. then we have to check whether the given series is convergent at this point or not. So let us see the convergence at the end point. At z is equal to 1. So I have to put z is equal to 1 in this series. So the series becomes summation n is from 1 to infinity, and this is now 1 power n is 1, so 1 divided by n. I have to check the convergence of this series. So I can use different tests. Here I use the integral test. By the integral test, I have to write this 1 over x dx, where integral, the limits are from 1 to infinity. If I integrate this, I will get log x from 1 to infinity, and you can see that log infinity is infinity. So the given power series is divergent at z is equal to 1. So this point is not included in the interval. Now let us see that whether the given series is convergent at this point or not. So let us put z is equal to minus 1 in the given series. So at z equal to minus 1, we get that summation minus 1 power n divided by z power, divided by n, where n is from 1 to infinity. And you can see that this is an alternating series. And if I find the absolute convergence from the absolute value, I will get 1 over n, and this will be divergent. So it is not absolutely convergent. So what I have to do, I have to use the alternating series test. What is the alternating series test? We say that an alternating series must be convergent if it satisfies two conditions. The first condition is that if I take limit n approaches to infinity of an, the answer must be equal to 0. The second condition is that this must be non-increasing. Non-increasing means that n plus 1 must be less than an. So let us see whether it is conditionally convergent or not. So this is called conditionally convergent. So again, here an is equal to 1 over n. And if I take the limits, so limits n approaches to infinity, an is equal to 0. So the first condition is satisfied. And now let us see the second condition. From 1 over n, I can say that if I divide 1 by n plus 1, and on the other hand, if I divide 1 by only n, then this must be less than 1 over n, which means that an plus 1 is less than an. And this means that the second condition is satisfied. So this implies that summation minus 1 power n divided by n, where n is from 1 to infinity, is conditionally convergent. Okay, so now this point the series is convergent at minus 1. So what will be the interval of convergence? So in this case, the interval of convergence is given by interval of convergence. This is minus 1 is less than or equal to z, and z is less than 1, because it is not convergent at that point, but the series is convergent at minus 1. And we can also write that the series is convergent in this interval. That's all. So till the next lecture, Allah Hafiz, Assalamu Alaikum.